Imagine it is 2 a.m. Your AI agent just pushed a performance optimization that passed every automated test in your CI/CD pipeline. The deployment is green, CPU usage is within normal bounds, and your standard health checks are returning status 200 OK. However, deep within your distributed system, a logical inconsistency is silently corrupting data. Because the AI misunderstood a subtle edge case in your business logic, transactions are failing only for a specific subset of international users. Traditional monitoring, the dashboards we have relied on for a decade, is completely blind to this. It sees aggregates, not individual wide events that carry the necessary context. This is the new reality of AI-generated code. Failures are no longer loud crashes. They are quiet, expensive drifts into logic chaos. By the end of this lecture, you will learn how to turn this invisibility into absolute clarity and prevent these silent killers before they impact your bottom line. But why exactly do our current dashboards fail to see these AI-driven anomalies? To survive the era of AI-driven development, we must fundamentally shift our mental model. We are moving from simple monitoring to a framework built on Observability 2.0. This involves leveraging the Model Context Protocol, or MCP, to bridge the gap between the LLM that writes the code and the actual systems that run it. We need a system that does not just alert us when something is broken, but provides enough high-cardinality data for an AI agent to self-heal the very infrastructure it manages. We are talking about structured events that contain hundreds of dimensions: every user ID, every version tag, and every prompt iteration. This framework is no longer a luxury. It is a technical requirement for any organization letting AI touch their production code. We are building a feedback loop where observability becomes the nervous system for your autonomous agents, allowing for automated diagnosis and remediation. Now, you might ask, why isn't the current 3 pillars approach enough for this new agentic world? For years, we have preached the 3 pillars of observability: metrics, logs, and traces. But in a world where AI agents are generating thousands of lines of code per minute, these pillars have become isolated silos. Metrics aggregate data, losing the fine-grained detail needed to debug an agent's subtle logic flaws. Logs are often too unstructured and expensive to search at scale when an incident is unfolding. Traces provide the execution path, but often lack the rich state data of the AI's decision-making process at the time of code generation. This Observability 1.0 approach was designed for humans writing static code, not for dynamic, agentic environments. When an AI makes a change, the explosion of possible failure states increases exponentially. We need a unified data structure that combines these elements into a single, searchable record of truth that provides the full way behind every system action. The secret to solving this lies in a concept that most legacy tools struggle to handle: cardinality. High cardinality is the ability to track unique, individual elements like a specific transaction ID, a unique AI model version, or a specific prompt hash across your entire system. Traditional time series databases fail here because they struggle with the dimensionality of modern data. They want you to limit tags to keep costs down. In Observability 2.0, we move away from pre-aggregated metrics and toward wide events. A wide event is a single telemetry record that captures everything: the system state, the AI prompt that generated the code, the specific library versions, and the exact user context. When an AI-generated bug occurs, you do not look at a dashboard. You query these wide events to find the needle in the haystack instantly. This level of detail is what allows for true self-healing, because if an AI agent can see exactly what went wrong in high resolution, it can generate a fix with 100% confidence. But how do we practically transition from our current dashboards to this event-driven world? That's what we will explore in the next chapter, the shift to Observability 2.0. In the world of Observability 1.0, we lived in the silos of metrics, logs, and traces. When AI-generated code causes a production spike, looking at a CPU metric or a disconnected error log tells you nothing about which LM model version or which specific prompt caused the mess. Observability 2.0 shifts this paradigm toward wide events. A wide event is a single, deeply structured record that captures the entire state of a request, including custom dimensions like user id, feature flags, and even the specific AI agent metadata. Instead of trying to join disparate data points during an incident, you have one high-fidelity of event that contains all the way behind the what. In the 2026 production environment, where code changes are near instantaneous due to AI agents, this structured richness is the only way to maintain a source of truth. It allows SREs to ask arbitrary questions about the system without having to predefine indexes or predict failure modes in advance. But how do we pass this context across distributed AI microservices without losing a single bit? This requires a standardized transport layer that we will explore next. To support this massive influx of contextual data, the industry has standardized on OpenTelemetry, or OTel. In an AI-assisted development workflow, OTel acts as the nervous system. When an AI agent pushes a code change, the OTel SDKs must be automatically configured to propagate context across every service hop. This isn't just about tracing anymore. It's about the context propagation of agentic intent. We use the OTel collector to receive, process, and export these wide events to specialized backends. By 2026, the OTel semantic conventions have expanded to include AI-specific attributes, such as token usage, LLM latency, and hallucination scores. This stack ensures that every piece of code, whether written by a human or generated by an agent, speaks the same observational language. It provides the infrastructure necessary to stitch together the story of a request as it traverses through a sea of autonomous services. Adding all this rich metadata sounds great, but won't it explode our storage costs and slow down our queries? Question: let's look at how the underlying storage handles this data explosion. The biggest fear in traditional monitoring was cardinality explosion, the idea that having too many unique tags, like user IDs or container hashes, would crash your database. In Observability 2.0, high cardinality is no longer a bug, it is a fundamental requirement. Modern observability backends use columnar storage and intelligent indexing to handle millions of unique values effortlessly. While 1.0 architectures struggled with pre-aggregated metrics that lost detail, 2.0 architectures embrace raw, granular data. This is critical for AI-generated code because failures are often long-tailed. They only happen for a specific version of a model under a specific load condition. If you aggregate your data too early, you lose the evidence needed to fix the hallucination. By comparing 1.0 and 2.0, we see a shift from monitoring for known unknowns to observing for unknown unknowns. We've built the foundation, but how do we apply this specifically to the lifecycle of code created by an AI agent? Teaser: the answer lies in how we govern the agentic lifecycle itself. In the era of AI-assisted development, observability cannot be an afterthought. It must be injected into the very beginning of the pipeline. The agentic lifecycle starts with generation, moves to automated validation, and ends with deployment. At each stage, we need observability gates. During generation, we observe the LLM's prompt context to ensure the agent has the right information. During validation, we use tracing to observe how the AI-generated code behaves in a sandbox. We don't just run unit tests. We run observability tests to see if the code produces the necessary spans and events for production monitoring. If the code is dark, meaning it has no instrumentation, it is rejected before it ever hits a server. This proactive governance bridges the gap between the speed of AI coding and the stability required for SRE. Even if the pipeline is solid, the code itself must behave differently. How does LLM written differ from human written code in terms of instrumentation? Payoff: let's look at the actual code structure. Human developers often write code with intuitive error handling, but they frequently forget to add telemetry. AI agents, conversely, can be prompted to follow a telemetry-first pattern. However, without strict templates, LLM-generated code tends to produce generic try-catch blocks that hide the real root cause. In Observability 2.0, we enforce a pattern where the AI must wrap every logical unit in a named span with specific attributes. Look at this comparison: a standard function vs an agent-instrumented function. The agent-instrumented version doesn't just return a value. It records the input's hash, the processing time of internal AI calls, and handles exceptions by attaching the full error stack to the event. This level of detail is what makes self-healing possible later. If an agent is writing its own instrumentation, can we actually trust its self-diagnosis? Question: this brings us to the critical problem of the trust gap. The ultimate challenge in 2026 is the trust gap, the space between an AI agent's autonomous action and an SRE's confidence in that action. We adopt the trust but verify principle. This means we allow AI agents to generate and even deploy code, but only if they are wrapped in observability guardrails. These guardrails act as an independent supervisor, monitoring the output of the agent and comparing it against historical system norms. If the observability data shows a deviation, even if the code passes traditional tests, the guardrail triggers an intervention. We shift from passive monitoring to active governance. This is where the platform engineer's role evolves into agent governor. To move from just watching failures to having the AI fix them itself, we need a universal language, and that is where MCP, the Model Context Protocol, comes in. Bridge: in the next chapter, we will see how MCP acts as the bridge to true self-healing systems. In the production environments of 2026, the biggest bottleneck for AI agents isn't their reasoning capability, but their context blindness. An agent might generate a high-performance database query, but it has no idea that the target RDS instance is currently undergoing a failover or that the IOPS limit has been reached. This is where the Model Context Protocol, or MCP, becomes the critical missing link. MCP provides a standardized interface that allows AI models to securely discover and interact with external data sources and tools without custom, brittle integrations. Instead of hard-coding API calls to Prometheus or CloudWatch, the agent uses the protocol to ask the environment for its current state. By the end of this chapter, you will understand how this protocol transforms a passive observer into an active, self-healing system. But why is this protocol gaining so much traction over traditional REST APIs? Let's look at the underlying architecture that makes it special. To bridge the gap between high-level reasoning and low-level system metrics, we look at projects like OpenTrace, which has matured into an ecosystem over 75 MCP-compatible tools. These tools allow an agent to perform complex health checks, such as verifying pod stability in Kubernetes or checking for memory leaks in a specific Java thread, all within a single conversation turn. In the past, an SRE would have to manually correlate logs from one dashboard with traces from another. Now, the agent acts as the operator, using these MCP tools to gather wide events and deep traces instantly. This stack isn't just about reading data. It's about providing a structured vocabulary for the infrastructure. When an agent queries a system health tool via MCP, it receives a semantic response that it can actually interpret to make a decision. This sounds powerful, but how does the actual flow of a tool query work when a service starts failing? Let's trace a real-time request. When a production incident occurs, the integration flow between the AI and the MCP tool follows a strict call, execute, observe cycle. First, the agent identifies a need. For example, it notices a latency spike and wants to check if the connection pool is exhausted. Instead of an SRE typing a command, the LLM emits a tool call request via the MCP. The local MCP client receives this, executes the specific health check against the production environment, and returns the structured JSON output to the agent. Crucially, the agent doesn't just see the raw numbers, it receives the context of what those numbers mean relative to the service's baseline. This tight loop allows for rapid-fire troubleshooting that happens in milliseconds rather than minutes. We're moving from a human-in-the-loop to a human-on-the-loop model, where the agent does the investigative legwork. However, for this to work, the agent needs a complete map of the environment to avoid tunnel vision. Let's see how that map is constructed. The true power of MCP lies in its ability to centralize a fragmented ecosystem. In a modern SRE min-map, we see the agent at the center, connected to code repositories, log streams, and infrastructure metrics simultaneously. This agent environment creates a holistic view where a change in a Git commit can be directly correlated with a surge in FIFAX errors in the logs. MCP serves as the radial branches connecting these disparate data silos. By using standardized MCP servers for GitHub, Slack, and Datadog, the agent can notify the team, analyze the faulty code, and check the impact on the cluster all at once. This isn't just about efficiency, it's about accuracy. Without this unified context, an AI might suggest a fix that solves a symptom but breaks a dependency it didn't know existed. Now that we have the infrastructure bridge in place, how do we use it to actually fix things automatically? Let's dive into the self-healing loop that defines the next era of operations. The Superlog pattern is the evolution of the traditional log analysis. In the self-healing loop, we don't just alert on an error, we trigger an agentic workflow. When a wide event captures a high cardinality failure like a specific user hitting a null pointer exception, the agent immediately consumes this Superlog. It uses its reasoning to hypothesize the cause, then employs MCP tools to verify that hypothesis against the code and the current environment. If the hypothesis is confirmed, the agent generates a targeted auto-fix patch. This is the detect, analyze, fix cycle powered by AI. It turns the passive data of Observability 2.0 into an active response mechanism. Instead of waiting for a human to wake up at 3 a.m., the system attempts to resolve known error patterns autonomously. But can we trust this AI-driven recovery more than a human operator? The data suggests we might have to, considering the speed of modern deployments. Comparing manual bug fixing with AI-driven self-healing reveals a dramatic shift in MTTR, or mean time to recovery. In a traditional scenario, even a skilled SRE spends the first 15 to 30 minutes simply gathering context, finding the right logs, checking recent commits, and ruling out infrastructure issues. An AI agent, leveraging MCP, performs this context gathering in seconds. While the human is still logging into the VPN, the agent has already performed a binary search on recent deployments to identify the bad commit and verify the failure path using trace data. We are seeing recovery times drop from hours to under 5 minutes for common failure modes. This doesn't replace the SRE. It frees them to focus on architectural black swan events while the agent handles the known unknowns. But this speed comes with a danger. What if the AI's fix makes things worse? This is why safety gates are not optional, they are the most critical part of the architecture. Before any agent applies a self-healing patch, it must pass through a series of rigorous safety gates. Think of this as the Hippocratic Oath for AI agents. First, do no harm. In 2026, a standard safety gate includes a semantic analysis of the proposed patch to ensure it doesn't introduce security vulnerabilities, followed by a canary application where the fix is only deployed to 1% of traffic. We also require a rollback strategy. The agent must prove it can revert the change instantly if the error rate doesn't drop. These gates aren't just technical, they are policy-based constraints defined by the platform team. If the agent cannot find a fix with a high confidence score, it must escalate to a human immediately. This controlled autonomy is what makes self-healing safe for enterprise production. Do you have these gates defined for your agents? If not, you are one hallucination away from a total outage. Let's summarize how we transition from watching to acting. To wrap up this chapter, we have seen how MCP transforms observability from a passive watching activity into active intervention. By providing AI agents with a standardized way to query system state and execute operational tools, we bridge the gap between AI-generated code and the harsh reality of production infrastructure. The self-healing loop powered by wide events and the model context protocol represents the pinnacle of SRE maturity in the age of AI. However, there is a catch. All of this sounds perfect in theory, but does it actually work in a messy, legacy-filled real world? In the next chapter, we are going to look at the benchmarks and reality check. We'll look at actual performance data of these agents and see where they fail when the protocol isn't enough. It's time to separate the 2026 hype from the hard engineering reality. In the early adoption phase of 2025, we saw a massive performance gap between traditional monitoring and Observability 2.0. Looking at the data from the Superlog and OpenTrace community projects, teams that integrated AI agents with wide events reported a 40 pentafaster mean time to recovery. Why? Because agents didn't have to waste tokens parsing unstructured log strings. They ingested high-cardinality JSON data directly via the Model Context Protocol. In real-world scenarios, this meant the difference between a 30-minute outage and a 2-minute automated fix. However, the data also reveals a harsh reality. Teams without structured telemetry saw no improvement, as their agents spent more time guessing than observing. High-fidelity data is no longer a luxury. It is the fundamental fuel for AI-driven operations. But speed is only half the story. What happens when the AI sees things that aren't actually there? This brings us to the most dangerous failure mode in autonomous SRE, the hallucination loop. The most dangerous scenario in an AI-driven environment is the hallucination loop. Recent industry postmortems have highlighted cases where agents misinterpreted background noise in high-cardinality metrics as a catastrophic failure, triggering unnecessary infrastructure rollbacks or even cluster deletions. When an AI agent lacks the grounding of wide events, it fills the contextual gaps with statistical probability, which is often wrong in complex distributed systems. This agent hallucination is the primary reason why many organizations still hesitate to grant full access via MCP. Without proper guardrails and a semantic understanding of your system's health, an agent can become a liability rather than an asset. We must treat agent suggestions as hypotheses that need validation through the same observability data they use to generate them. Payoff. This leads to a massive hidden cost that many platform teams overlook until the storage bill arrives. Let's address the elephant in the room, the observability tax. Storing high cardinality, wide events is expensive, often 3 to 5 times more than legacy sampling methods. However, the 2026 reality check shows that the ROI is calculated in human minutes saved. If an AI agent resolves a high-priority incident in 2 minutes instead of a human taking 45 minutes, the business savings and downtime and developer focus far outweigh the cloud storage costs. The strategy has shifted from store everything cheaply to invest in high-quality data for AI consumption. We are seeing a move toward tiering telemetry data, short-term high-fidelity storage for AI agents, and long-term compressed archives for compliance. In 2026, storage is a commodity, but system availability is the ultimate competitive advantage. But even with a clear ROI, why are some of the world's best engineering teams still pushing back against this automation? The SRE community sentiment is currently split. There is significant pushback regarding autonomous infrastructure. Many veteran engineers argue that giving an AI agent full control over production via MCP is a security nightmare. They fear the black box problem if an AI fixes a problem, but we don't know why. We haven't actually improved our system's resilience. The common skepticism centers on accountability. Who is responsible when an AI-generated fix causes a downstream failure? Consequently, we are seeing a shift toward advisory agents rather than autonomous agents. In this model, the AI performs the heavy lifting of data analysis and presents 3 validated options to a human engineer. This hybrid approach balances the speed of AI with the critical judgment of a human SRE. Teaser, this cautious approach is the bridge to our next major milestone, the 2026 roadmap. Looking toward the end of 2026, the roadmap is clear: the total convergence of AI agents and platform engineering. We are moving away from reactive dashboards and toward intent-based infrastructure. In this world, you don't write code to scale a service. You define the desired state, and AI agents, powered by the Model Context Protocol and wide events, continuously reconcile the reality with that intent. We will see the emergence of observability as code, where telemetry is automatically injected into every AI-generated PR. The benchmark of a senior SRE will soon be their ability to build the guardrails that allow these agents to operate safely at scale. We've moved from monitoring things to observing things to having systems that explain themselves. Bridge, now that we understand the benchmarks and the reality, how do you actually build this? In the next chapter, we will dive into the implementation strategy for 2026. By 2026, simply monitoring CPU and memory is obsolete. To manage AI-generated code, your stack must bridge the gap between raw telemetry and LLM reasoning. The core of this architecture is the Open Telemetry (OTel) collector integrated with a Model Context Protocol (MCP) server. The OTel collector acts as the universal ingester, gathering wide events and distributed traces from your infrastructure. The MCP server then acts as a sophisticated context provider, allowing AI agents to query this live telemetry data in a structured way. This allows the agent to not only see that a service is down, but to understand the deployment history and the specific code diffs that caused the failure. We are moving from a passive dashboard culture to an active contextual intelligence layer. This setup ensures that when an agent suggests a fix, it is grounded in the current reality of the production environment rather than outdated documentation. However, setting up the pipeline is just the beginning. The real challenge lies in how we capture the agent's internal decision-making process. But wait, how do we actually wrap these complex AI interactions into a format that a standard SRE tool can understand? Let's look at the instrumentation layer. To observe an AI agent, you must treat the LM call as a critical transaction. In 2026, we use wide events to capture the full context of an agent's thought process. This boilerplate code demonstrates how to wrap an AI agent's execution within an open telemetry span. Notice how we are not just logging the output. We are attaching rich metadata such as the model version, temperature, prompt tokens, and most importantly, the agentic reasoning trace ID. By using the trace get current span method, we inject attributes that allow SREs to trace back a production failure directly to a specific hallucination or logic error in the agent's code generation. This level of granularity is what separates a toy project from a production-ready AI development pipeline. We use the OTel semantic conventions for GenAI to ensure that our telemetry is standardized across different models and vendors. This programmatic approach allows us to build automated feedback loops where the system detects an error and automatically feeds the trace back to the agent for a second attempt. But even with perfect data, the question remains, when should we actually allow the agent to press the fix button without human intervention? This leads us to our next critical decision framework. Not all production issues should be handled by AI. In 2026, SRE teams use a risk-based automation matrix to decide between human-in-the-loop and fully autonomous self-healing. We categorize actions into 4 levels based on their blast radius and reversibility. For low risk, highly reversible tasks like horizontal scaling or cleaning up temporary disk space, we can move toward level 4, fully autonomous. However, for high-impact actions like database schema migrations or stateful service restarts, we strictly enforce level 2, human-in-the-loop, where the AI suggests the solution but a human must sign off. The AI's confidence score is another key metric. If the MCP server reports a high uncertainty in the telemetry data, the system must automatically downgrade the automation level. This framework prevents cascading AI failures, where an agent might try to fix a symptom but accidentally triggers a larger outage. This is not about trusting the AI less, but about designing a system that respects the laws of distributed systems. Does your current platform have the necessary guardrails to support these different levels? Let's check the final readiness requirements. Before you enable MCP-based agents in your production cluster, you must pass the operational readiness checklist. In the world of 2026, SRE is synonymous with governance as code. First, you must ensure that your MCP server has strict RBAC, role-based access control. Define the AI should only have the permissions it absolutely needs. Second, you must implement circuit breakers for the agent. If the agent attempts more than 3 failed remediations in 10 minutes, the system should lock its access. Third, verify that all AI actions are tagged with an owner or trace ID for auditing purposes. We are not just building for speed, we are building for accountability. Without these guardrails, AI becomes a liability rather than an asset. By checking these boxes, you transform your platform into a resilient environment where AI can safely innovate. This implementation strategy marks the transition from traditional SRE to the new platform architect for AI. But what is the final destination of this journey? In the concluding chapter, we will look at the long-term future of the SRE role and how you can stay ahead in an industry defined by autonomous code. The era of the SRE being a mere watcher of dashboards is officially over as we enter 2026. With AI agents now capable of generating and deploying code at a velocity humans cannot match, your role must evolve into that of a governance architect. You are no longer just fixing bugs. You are designing the very telemetry pipelines and wide event structures that allow AI to understand its own impact. By 2026, the SRE's primary value lies in defining the MCP-based boundaries, the policy as code that prevents an autonomous agent from cascading a minor latency spike into a global outage. If you don't build these guardrails using Observability 2.0, you aren't just managing a system, you're babysitting a chaos engine. Think of it as moving from being the driver to being the city planner who designs the traffic laws and sensor networks that keep autonomous vehicles safe. But how do we distill this massive shift into immediate, actionable decision points for your next sprint? Let's wrap up with the final roadmap. As we conclude this lecture, remember that the intersection of AI-assisted development and Observability 2.0 is the most critical frontier for the 2026 SRE. We've explored how AI-generated code increases technical debt and operational risk, and why legacy logs are insufficient to describe the high-cardinality mess created by autonomous agents. The solution isn't to stop AI, but to empower it with the Model Context Protocol, MCP, so it can perform self-healing within the constraints you set. We've looked at the transition from 1.0 metrics to 2.0 wide events and how to integrate MCP servers for real-time health checks. Your next step is to evaluate your current stack. Does it provide the context an AI agent needs to fix what it breaks? This series was the wake-up call regarding the risks. Now it's time to build the solutions. This marks the end of our risk analysis, but it's only the beginning of our technical journey. Stay tuned for our upcoming MCP deep dive series where we build a self-healing pipeline from scratch.